Have you ever wondered how we're really going to get to Mars and even beyond? Well, it's not just about building bigger and bigger rockets. It's about something way more fundamental, figuring out how to build a gas station in the middle of space. And that's exactly what we're digging into today, the incredible physics and wild engineering behind refueling in zero-G.
So a rocket like this could absolutely take us to Mars, but there's a huge hidden problem we have to solve first, and it's all about its fuel. You see, the real game changer for deep space travel isn't just launching bigger rockets, it's being able to refuel them once they're already in orbit. And to do that, we first have to solve some seriously weird physics. The secret to really powerful, really efficient rockets is using the coldest stuff in the universe as fuel. But these super-chilled propellants, as amazing as they are, create this massive engineering bottleneck when you're talking about long-duration missions into deep space.
We're talking about what are called cryogenic propellants. Think liquid oxygen, liquid hydrogen, liquid methane. These are gases that have been chilled to hundreds of degrees below zero to keep them in a dense, liquid state. The payoff is incredible efficiency. You get way more bang for your buck. The challenge, though, is keeping them from just boiling away into space.
Now, the reasons we go through all this trouble are huge. Using cryogenics can literally slash a spaceship's fuel system weight by 40%. That is a massive deal when every single kilogram costs a fortune to launch into orbit. So for the heavy lift rockets of the future and for this whole dream of in-space refueling, there really is no other choice.
And this isn't some theoretical problem. This phenomenon called boil-off is a massive waste of resources. I mean, just look at this. During the space shuttle era, over 50 million liters of liquid oxygen just vanished into thin air while the shuttles were sitting on the launch pad. Now, if that's what happens on Earth, just imagine how much worse it gets during a multi-year mission in the vacuum of space. Okay, so the problem gets even stranger once you leave Earth's gravity behind, because out there, liquids just stop behaving the way we expect them to. It's like they completely forget which way is down, and that creates a totally mind-bending puzzle for engineers to solve.
You see, here on Earth, gravity does us a huge favor. It pulls all the liquid fuel neatly to the bottom of the tank, leaving the gas, or the vapor, right at the top. It's simple, it's predictable. But in space, gravity is basically gone, and a much, much weaker force takes over, surface tension. The liquid starts clinging to everything, the tank walls, itself, and it can end up anywhere, often trapping the vapor in a giant, unpredictable blob right in the middle.
This little tug-of-war between gravity and surface tension is measured by something called the Bond number. But here's the crucial point. When you're in space, how do you pump fuel to an engine if your fuel pump inlet is just sucking up vapor? How do you even measure how much fuel you have left if it's just smeared all over the inside of the tank? The short answer is, you can't. Not without first understanding and controlling this totally bizarre zero-G behavior.
So, how do you possibly solve a problem that happens inside a fuel tank the size of a building, millions of miles from Earth? You can't just launch endless expensive experiments. The answer is kind of brilliant. You figure out how to test that huge tank on a tiny tabletop.
You do it with math. Incredibly clever math that lets you replicate the physics of a giant system in a tiny, manageable model, right here in a lab on Earth.
This is done using something called a scaling law. It's this powerful concept from what's known as similarity theory, and it's basically a recipe. It tells you exactly how to scale everything down, the size, the time, even gravity and heat, so that your little experiment behaves exactly like the full-size version would in space.
Now, for years, the scaling law for these systems was thought to be a pretty simple squared relationship, but it didn't work whenever the fluid was sloshing around, like it would during a refueling operation. But recent breakthroughs have produced a brand new, much more accurate law. This new relationship, where time is proportional to length to the power of 1.65, finally cracked the code for fluids in motion.
And the results? They are absolutely stunning. This new model can predict the pressure inside a full-scale tank with less than 5% error, just from studying a tiny tabletop model. That leap in accuracy, that is the real game changer here. It means engineers can finally design and test these complex systems with confidence right here on Earth, which dramatically cuts the cost and time it takes to get flight-ready hardware built. Okay, so with the science figured out, it's time to build the hardware. And this isn't just theory anymore. NASA and its commercial partners are actively building and flying the systems that are going to become our future interplanetary gas stations.
This right here is NASA's official roadmap for what they call cryogenic fluid management, or CFM. It's all laid out. We've got ground development happening now, flight demos coming up in the mid-2020s, and all of that is leading to a massive, large-scale flight demonstration before 2030. This is the clear path to getting this technology ready for Mars.
A huge part of making this happen is NASA's Tipping Point initiative. The whole idea is to fund commercial companies to help push these critical technologies, like in-space refueling, from the lab into actual flight-proven hardware. So, let's take a look at who's building what.
First up, SpaceX. They have a $53 million contract to demonstrate a massive on-orbit transfer, and we're talking more than 10 metric tons of cryogenic fuel between tanks on a single Starship flight. This is an absolutely foundational test for their entire Mars architecture.
Then you've got United Launch Alliance, or ULA. They're working on an $86 million project to demonstrate some key technologies on their Centaur V upper stage. If they succeed here, it could increase their rocket's performance by 20% and vastly extend how long their missions can last.
And other major players are deep in this race too. Lockheed Martin is working on demonstrating not just the transfer, but, and this is crucial, the long-duration storage of liquid hydrogen for up to 60 days. Meanwhile, a company called Eta Space is launching a dedicated satellite on a 9-month mission just to test over 10 different CFM technologies all at once. The entire industry is racing to solve this puzzle.
So what is the real end goal of all this research, all these contracts, and all this testing? Well, it's to build a fully functional, completely autonomous, interplanetary gas station. The next great leap is a full, large-scale demonstration. The goal is to prove once and for all that we can autonomously transfer and store tens of metric tons of the absolute trickiest cryogenic fuel, liquid hydrogen, with virtually zero boil-off loss. You can think of this as the final exam before we can build operational fuel depots in space.
And there's a really clear step-by-step plan to get there. First, you master the easier stuff, the liquid methane systems. Next, you evolve that technology to handle the much colder, much more difficult liquid hydrogen. And finally, you integrate everything into one complete system that's capable of full two-way transfer operations.
And that brings us to the final and most important question. If we solve this, if we master the weird physics of zero-G fluids and build these orbital depots, what does that truly unlock for us? Well, it's not just about refueling rockets. It's about enabling a sustainable human presence on the moon, it's about making missions to Mars routine, and it's about building an entire economy throughout the solar system. It really is the hidden key to our future in space.